engineering and bioengineering, and having worked with all these people like Richard Murray, Michael Dickinson, and Robert Woods, that you always come up with interesting insect-inspired and biomimetic solutions. So in the next talk, we'll talk about the actual control of a already fully working flapping wing device with pitch, yaw, and roll control. After you get the actuation to actually work, the work is not finished, and that's the subject of the next talk. Thank you very much.
Thank you. Okay. Does mic sound good? Is okay? Okay, cool. Okay. Yeah, so this talk is about how to integrate a gyroscope onto the Harvard RoboBee, which is a fly-sized micro-aerial vehicle. So the basic goal here is to, what I'm aiming for is to build a sensor package ultimately that will enable this robotic fly to now hover autonomously. And I need to give a little bit of background for anybody who missed the talk I gave on Tuesday, so I'm going to spend a couple minutes on background describing the robot. So sorry if you've already seen some of this material. So the robot that I will talk about in this work is this 80 milligram vehicle developed at the Harvard Microrobotics Lab under my advisor, Professor Rob Wood. It's fabricated out of carbon fiber and using this kind of novel ultraviolet laser-based fabrication process. It weighs about 80 milligrams, which is a little less than a typical honeybee. It flaps its wings at 120 hertz, and it actuates the two wings separately using an independent pair of piezo actuators, as shown on the right. The independent wings give it the ability to apply torques about orthogonal pitch and roll axes, and this allows free flight to be controllable. For example, to apply a roll torque, as a previous speaker was talking about, if the one wing is flapping with a larger amplitude than the other, this generates a differential force, which can cause a roll torque in this direction. And like a fly, this vehicle, when left to its own devices without any feedback control, is dynamically unstable. I'll show you just a couple videos, which you saw a couple days ago, of the vehicle in flight without any feedback. So needs some feedback. I will give a short overview of previous approaches used to control the vehicle before I'll go into integrating the gyro version. So previously, the first way we got control of this vehicle was using this set of external motion capture cameras. In this case, we had 8. And let's see, so that's the kind of diagram of the flight arena with the RoboBee in the middle. This is what it looks like. The red rings are the emitted light from the infrared cameras. There's the vehicle at the bottom. The 4 retroreflective markers are placed on the vehicle that reflect light from any incident direction directly back to the source, so that these cameras can notice these markers very easily and triangulate the position of the vehicle. This dark cloth makes the markers more visible or increases the contrast because these cameras are being used in a way that they kind of weren't traditionally designed for, and are much closer together than they normally are used. So after some head scratching and some tuning and calibration, you can devise this controller. Here's the controller doing a simple lateral maneuver using feedback from these external motion capture cameras. And so, as you know, in this flight demonstration, the vehicle itself has no sensors carried on board. So the goal is, the next phase is to fly without these cameras by incorporating sensor payload on board that will give this vehicle the ability to perceive the world. So more recently, we showed an example of the first example of doing onboard sensing using Ocelli-inspired light sensors. And what this project showed was that it was possible to stabilize the upright orientation of the vehicle using these sensors. So the result required a slightly more sophisticated model of the robot's dynamics than were used in the hovering controller I showed. So I'll go over that a little bit because we then use it for the gyro result later. So consider how the dynamics of the vehicle are affected by the flapping wings. So the flapping wings generate this lift thrust that keeps the vehicle aloft. If the robot is tilted, of course, then that thrust vector is tilted and a lateral force is induced. And this causes the vehicle to accelerate laterally. Now it has some lateral velocity, we'll call it Vx, at which point aerodynamic drag starts acting on the vehicle. Let's see. The aerodynamic drag will act on both, in principle, the wings and the body, but the wings have a relatively much larger surface area than the body does, and they also move much faster. So in this model, we basically assume that the drag on the body is negligible and assume that the drag is acting only at the wings. So in this diagram, I draw the wings extending kind of laterally parallel to the screen here, but they're in fact, of course, moving in and out of the screen by a large amount. So they have a large amount of, on the order of 90 to 110 degrees. So there's a lot of frontal area in the lateral direction as well as on the front direction. And wind tunnel tests of the RoboBee in a wind tunnel indicate that aerodynamic drag is proportional to airspeed for both the airspeed from the front and from the side. So the model is just, and it's actually about equivalent for typical wing kinematics. So the model is just that drag is proportional to velocity. And if you go through the math and assume drag is proportional to the velocity of a plate moving through the air squared, as is the case at this Reynolds number, if you do the math where you think about the downstroke versus the upstroke and averaged over a single wing stroke, that turns into a drag that's more or less on a stroke average basis proportional to the velocity and also proportional to the average speed of the wings. So in our case, with a typical wing speed, we can just abstract it to a constant. So this drag is acting above the center of mass. So it induces a torque around the center of mass, coupling the angular velocity and the lateral velocity. You can write out the you can write out the dynamics something like this. And now, if you substitute in parameters you can measure on the RoboBee, you find that this is an unstable system, supporting the intuition from the videos I showed earlier. So now suppose we add a controller that can apply a torque. It doesn't matter where the torque is being applied. It's actually applied by the wings, but you can think about it as going about the center of mass. Suppose this torque is in proportion to the center of mass. This, of course, would be done by altering wing kinematics in a known way, in a known mapping between signals and torques. You can use the Routh-Hurwitz stability criterion to find a lower bound on the gain necessary for stability. In terms of the parameters of this model, the equation itself is pretty complicated, so I'm not going to give it here. But that number is possible to find. And of course, okay, so now we have a controller, so we need an estimate of this angular velocity. So you can write the angular velocity estimate as a linear function of the derivatives of the Ocelli readings. And so this, I showed in the previous talk, was able to stabilize the vehicle using this feedback control law. The possible downside here is that to use the ocelli, the light source has to be somewhere above the vehicle, more or less. And this assumption usually holds indoors and outdoors, but you can easily think of situations where it doesn't really hold. For example, maybe you're flying indoors, but you're flying near a bright window with a view of the outdoor sky. In that case, the light source might generally be almost lateral to the vehicle. So this suggests that this could be a problem for an indoor flying vehicle like the RoboBee, and maybe there's a better approach here, or this is a possible failure scenario. Yeah. So in this talk, I consider a different sensor than the ocelli, but it provides potentially very similar feedback, angular velocity feedback. So okay, I don't say the manufacturer here. This is made by InvenSense, MPU 9150. It's a silicon microfabricated MEMS gyroscope that uses a resonator to measure gyroscopic Coriolis forces. These parts have only recently become small enough to fit and be carried by the RoboBee. This one weighs 37 milligrams. It also has an accelerometer and a magnetometer. A nice aspect of the magnetometer for the RoboBee is the RoboBee actually is driven by piezos, which have a very small amount of current going through them, basically no magnetic fields. So there's an interesting possibility that the magnetic field will be less disrupted by the RoboBee than in motor-driven aircraft. And we've done some, in a previous work, we showed that we could use a magnetometer in a feedback loop mounted right next to the actuators on the RoboBee. But I won't talk about that here. So, okay, so this is a sensor, 37 milligrams, gives pretty high bandwidth. We built this circuit board, weighs about 4 milligrams. And with these passive components, capacitors, solder actually makes a very large component of the weight of this circuit board. So together, the 4 milligram circuit board and the 37 milligram IMU weigh a total of 41 milligrams. And as I mentioned, the vehicle itself is about 80 milligrams. So this is adding more than 50% of the mass of the vehicle. And this potentially could be a challenge because this is a significant increase in mass. Another thing we had to do was to integrate the IMU with our control computer. So we typically use XBC Target to control the RoboBee. This is a kind of a real-time operating system that runs on a desktop PC that basically runs Simulink models. And so the IMU only speaks I²C. Turns out it's kind of difficult to get an XBC Target PC talking I²C. We had to go to this company in Switzerland that called SpeedGoat that really likes fast goats, apparently, to build this FPGA solution that implements this protocol. So this is what the IMU looks like mounted onto the top of the vehicle. Initially, we tried attaching it to the side rather than the top. The idea was to bring it as close as possible to the center of mass of the vehicle. What we found when we had it mounted there was that this induced a very large torque that was too much for the wings to overcome, so we had to put it on top. In future designs, future iterations of this will actually have space in the middle between the actuators to put the IMU. But for now, this design was not made with incorporating IMU in mind. So the first question was, can this vehicle carry an additional 50% payload? And this had never been tried before. And one of the challenges here is that the way the RoboBee works is you have lift headroom, so extra headroom in your ability to generate lift. And this can be variously used to generate more lift or to generate larger control torques, but there's kind of a zero-sum game. If you use all of your lift headroom to just generate enough lift, you have no room left to generate control torques. So we might have generated enough lift, but not had any room to control the vehicle. So in this video, this was the first thing we tried, was just lifting off with no control torque. So it was an open loop. In this case, the vehicle we found much to our delight, that it could actually carry the gyroscope. So we were off to the races. And as you've seen in the other videos, the robot exhibits the same dynamic instability, and it does immediately crash. And this is a consistent behavior, even if it's carrying the IMU on the top. So the next step was to ask what the flapping effect, what effect the flapping had on the robotic, on the gyroscope. So in our case, the vehicle's flapping at 120 hertz, and this induces a fairly large amount of vibration. Previously, the creators of the Nano Hummingbird, which is a larger flapping wing vehicle, which is 20 grams, so a few orders of magnitude heavier, but they had reported that certain models of gyroscope were significantly, had their readings significantly disrupted by the vibratory environment of their vehicle. And their wings were only flapping at 20 hertz, whereas ours is 120 hertz. So there was, it's possible that these relatively larger vibrations could cause even more disruption. So we wanted to see if this was going to be a problem. So we recorded data from the gyroscope during a short flight, controlled by the motion capture system. So as you can see on the top plots, the gyroscope is reading large oscillations around all three axes. The three different colors are the three different axes at the 120 hertz flapping frequency. By filtering with a simple low-pass filter, which are shown, the results of which are shown in the thick lines, this oscillation is substantially removed. And then we went and compared the estimate from the gyroscope to that of an estimate derived from the motion capture system. And the two match with quite good fidelity. The motion capture estimate is a thin line, and you can see it's slightly offset relative to the gyroscope feedback, on the order of 10 to 15 milliseconds. So this is consistent with the idea that the motion capture has a 10 to 15 millisecond latency. And this is kind of a nice feature of the gyroscope, because it promises then that it has a lower latency, which could be useful for doing more aggressive or rapid maneuvers. Next, we looked at the accelerometer reading, just out of curiosity. So this is the accelerometer reading during the initial phases of a takeoff flight. And what you can see is that the green line has the biggest oscillations. And this is consistent with the intuition that the acceleration in the front-back direction, which is the green direction here, is relatively largest, because the wings are doing this sort of motion. So the gyro or the accelerometer is moving front and back like this. These oscillations are as much as 50 meters per second, or about 5 Gs. So this is, I would say, a pretty large acceleration. So then, looking at a longer time scale during a hover flight, this is the Z measurement. So the vehicle took off, accelerated to a set point height, and then remained there. We compared the motion capture acceleration estimates to those of the accelerometer, and the thin line is the motion capture estimate. The noisiness is just because we're taking two derivatives. And the thick line is the equivalent reading from the accelerometer after the same low-pass filtering. Compared to the motion capture, the accelerometer reading, so at the beginning you can see they're both at 0 before the wings start flapping. You can see that the accelerometer is reading roughly a meter per second error in the negative direction relative to the true value from the motion capture system. You'll also notice that the signal of interest is about a meter per second. So the error is as big or bigger than the signal of interest at this point. So this suggests that there's some distortion in the accelerometer reading, possibly due to nonlinearity in how it's reading data over large ranges of 5 Gs. So we decided for the moment that this would require more processing, and in this work, we did nothing more with incorporating the accelerometer and left that to future work. So the next thing was to think about the simplest thing we could do with the gyroscope. So we started by applying only angular velocity feedback from the gyro to provide upright stability. So this uses the same result I described from the Ocelli work with the same gain as well. And what this shows is that using just angular velocity feedback from the gyroscope, the vehicle is able to remain upright during short flights. And in this video, the position was not under feedback control. This is the trajectory. The dots are the center of mass of the vehicle, and the lines are the kind of the long axis of the body. And then the gray is the projection on the different XZ and YZ axes, as well as the projection from above. So next, we then wanted to advance beyond this kind of demonstration from the Ocelli and upright stability and incorporate gyroscopic feedback into the previously working controller we had to do hovering. So this controller requires feedback about the following information. First, angular velocity given in body coordinates. Second, the set of Euler angles. And then thirdly, the position of the vehicle in space. Okay, so to perform this experiment in which the gyro started giving some of this information, we started by verifying whether the motion capture, using motion capture, now we could control hovering, carrying the gyro. So we had to retune the gains a little bit, increase the gains because the moment of inertia was increased by about a factor of 2 with this extra mass, or actually factor of 3 with the extra mass of the gyro on the top. And with this little bit of tuning, we were able to get the vehicle to hover successfully under motion capture. So then the next step was to start incorporating the gyro. So in this video, the gyroscope now provides angular velocity feedback used by the controller, but the motion capture is providing the absolute attitude estimate as well as the position of the vehicle in space. Sometimes the takeoffs are not quite as consistent. Down near the ground, the tether has a relatively larger effect, and so it can destabilize the flight during takeoff. I don't think that was the fault of the controller, just the configuration of the wire tether. So by the way, there's 4 wires going to the actuators in this video, and then another 4 of the same size, 51 gauge copper wires going to the IMU. And luckily, I2C works over these tiny wires. So this is generally working pretty well. We had slightly higher incidence of wing breakage because of the added weight of the gyroscope on top, and had to replace wings a couple times. As you can see here, the flight trajectory stays very much in the vicinity of the desired set point, as shown by the red circles in these projections. So finally, we additionally use the gyroscope to estimate the attitude of the vehicle by numerically integrating its estimate over time to provide Euler angles. So what you see is, for the first 2 seconds, more or less, the performance is actually pretty good, and it's able to hover. After a little bit, however, it starts losing altitude. And this is probably because of drift in the estimates from the gyro. After a certain amount of time, the controller shuts off, and the vehicle lands by luck. So this is the readings from the gyros over time. The Euler angles estimated over time, and what you can see is there's a little bit of drift. But for the first 2 seconds, the vehicle hovers pretty successfully near the set point, though with a larger error than in the previous case, presumably because the estimate was not perfect during the time. So with that, I'll just summarize what I showed you here. This is about integrating a MEMS IMU onto a flapping wing vehicle. The attitude estimate enabled short hovering flights, but the accelerometer was slightly disrupted, so we could only use the gyro in this work. In the future, a couple steps. I think a Kalman filter could possibly reduce this drift using the incorporation of a different sensor. There's a newer IMU that is smaller, only 23 milligrams. That's a savings of 15 milligrams, which would be pretty awesome and could allow the incorporation of an additional sensor. This also kind of provides the stable baseline platform for stability that can be additionally allow now even sensors such as vision to be incorporated, so we can move on toward higher levels tasks such as navigation. So with that, I'd like to thank my co-authors, Farrell, Pakpong, and Rob Wood, sponsors of this research, and the organizing committee and crew for IMAV. Thank you.
Well, thank you, especially. Your work is really redefining the definition of small, and is definitely an inspiration for future IMAVs. So if even our smallest gyro is half your weight, that's something to consider. Are there questions in the room?
Yeah. Oh. So the question was, how's the filtering done? In our case, we just, yes, I think the sensor has the ability to do its own filtering. In our case, we wanted as much flexibility and control, and with a desktop computer, we kind of have infinite computation resources for these purposes. So we just do it on the desktop computer. And yeah, it's a low-pass filter. More recently, I've used and switched to using a notch filter, which gives a little bit better performance and lower latency.
Other questions, please?
Adding to the previous question, did you try to use the onboard filter?
So the question is, did we try to use the onboard filter? No. 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 That would require looking up more registers and doing things that I'd rather be flying robots instead.
Please, in the middle.
You decided to place the sensor on top,
Yeah.
instead of on the bottom.
Yeah.
So you place more weight above or you raise the center of mass.
Yeah.
And it's also at the most vibrating.
Yeah. Yep.
So why did you decide to put it there instead of at the bottom?
Good question. So the question is, why put the sensor at the top of the robot where there's the most vibration than at the bottom? We had a couple reasons for doing it. One is that there's a lot of wires coming from the actuators at the bottom, and it's nice to be able to reach those because inevitably the wires tear off, and if you have IMU sitting there, that makes repair more difficult. The other reason is I had a faint, so if you run the model suggests that if the center of mass is close enough to the wings, it actually becomes dynamically stable. So I had a faint hope that by adding all this mass at the top, it might actually stabilize it, but it didn't. So to finish the thought, I've started using the smaller IMU, and we now have it at the bottom, and the acceleration, these vibrations are reduced by about a factor of 2 to 3. So that's what we're going to stick with now. Yeah.
Now another question for Rick.
First to go on the filtering, are you
Yeah.
sure you don't have
So the question is, are we sure we don't have saturation? Yeah, you can look at the feedback, and there's a pretty clear saturation, and it has different output ranges, and so we had to crank it up just above the range where it's saturated. So we're using most of the saturation availability for the accelerometer, but I think one step down for the gyro.
On the point of the center of mass,
Yeah.
there are other systems with a like this, which have explicitly their center of gravity above the center of lift, which would make,
Oh.
and also the nano hummingbird has the center of gravity quite high,
Huh.
and also
Above?
the moment of inertia intentionally made high by having one battery low and two batteries on top to make the stability problems less prominent.
Huh. So let's see. That was let's see, I don't know if I, what's the comment? Comment was the nano hummingbird has a large movement of inertia by moving the battery and motors as far away as each other as possible, and that helps them stabilize maybe because the dynamics are slower.
Also have the center of gravity above the center of
And the center of mass is above the wings. And is that, so what I read from their paper, they didn't give many details, which was a little bit annoying. But they said that, I think they said that they needed the gyroscope feedback to stabilize it. And it was unstable without gyro feedback. So, but you're saying that the center of mass was above the wings? Yeah. Huh. Yeah, interesting.
May I ask a last question? Are you using sensor fusion between the gyroscopes and the motion capture already? Or are they rather separated?
In this study, there is no sensor fusion between motion capture and the gyros. That's what I've been working on now, is making a Kalman filter that's kind of the next step, is to do that sensor fusion. And that should give us reduction of drift and
no drift and no delay. Reduced delay compared to the motion.
I think the delay is about the same with a Kalman filter, but yeah. Yeah.
Well, I'd like to thank the speaker very much for presenting. Again.